Continuing our discussions about the connections between linear motion and rotational or angular motion, we discussed in an earlier video how force causes the changes for linear motion and how torque causes change for angular motion. You can see how then these formulas that we used when we discussed impulse can be translated into these formulas. The P becomes an L, and the F becomes the tau for torque. And also, something that we didn't mention earlier is how if you have an integral form of a formula, how that can be rearranged into a derivative. And so we can do a similar thing for angular motion. Tau is equal to dl dt. But this video mainly is going to discuss how, just like P is m times v, how L is I times omega. And then we will also talk or really show how that idea can be extended to a particle specifically, and how we get two other versions of this calculation for angular momentum. Our first example involves just a disk spinning on an axis, something that was talked about in the last video. And so in this case, to calculate L, we just need to know the I, the rotational inertia formula for this object, and the angular speed. And those are pretty much given to us. We have a little bit of work to do, but not too much. So first of all, we're going to convert the 80 revolutions per minute to the standard units of radians per second. So 1 minute on top versus 60 seconds, and then 1 revolution on the bottom versus 2 pi radians. And we end up with a value of 8.38 radians per second. So taking that and plugging it in along with the formula for I for a solid disk. Okay, a solid disk is 1/2 mr squared, so this formula becomes 1/2 mr squared times omega, or 1/2 times our 2 kilograms times our radius squared. We're going to make sure we're in standard units here, so we're going to take this 10 centimeters and convert it to 0.1 meters, and then divide that in half so we get the radius. So 0.05 meters squared. And then we're going to multiply that by this omega that we've converted. And that gives us our value of angular momentum. It's a pretty small number. That is pretty common for everyday objects that have fairly low speeds and fairly small masses. So 0.021 kilogram meters squared per second. The radians, of course, will cancel out. So that's our standard unit for angular momentum, kilogram meters squared per second. Not something to memorize, something to notice as you plug values into the formula. The direction of the angular momentum vector uses a right-hand rule. So looking at our picture, this object seems to rotate into the screen and then comes out of the screen over here. So if we were looking from above, it would be going in the clockwise direction. And if we rotate our fingers of our right hand in that direction, our thumb is forced to point down. And so that is the direction of the angular momentum vector, not clockwise, but down. Vectors point along a single direction. All right, in this problem here, we are looking for the angular momentum of a satellite. And the satellite isn't necessarily rotating, or a lot of people wouldn't think of it rotating. It really at any particular moment is traveling in a straight line, but that is part of a rotation about the Earth. And so it does have angular momentum about that point. And that's what we're going to try to find here. Let's just kind of look kind of generally how we will deal with particles. So if we look at our formula I times omega for L, if we have a particle, I is going to be just mr squared, no factor, no fraction. And a particle, typically, we will not be given the value of omega. We will be given a linear speed. But recall that for rotation, that v is equal to r times omega. So we can substitute v over r. Now, a lot of times with these sorts of questions, we will use this notation v perpendicular. That is to just kind of verify that this v is perpendicular to the radial direction. And again, you'll see in later problems why that's useful. So this L formula is typically written like this. L is equal to m times v perpendicular times r. Now, when you have that relationship, when you have two vectors where you always are taking the perpendicular direction between them, you can use a cross product to represent this. So what would happen here is that if we had a particle that was not moving perpendicular, say it was moving at some sort of direction like this, the angular momentum only depends on the perpendicular direction of that. And so we would, this formula still would hold as long as we made sure we grabbed that perpendicular direction. But another way to write that is to say that we want to take the cross product between these, between r and f, cross, I'm sorry, I wrote that in the wrong order here, r cross v, there we go. And a lot of times, because m times v is, of course, the momentum, this is written as r cross p. Okay, so these are your two general formulas that are often used with particles. Let's see how it works out with this problem. So if L is equal to mv perpendicular times r, that's usually the form that I like to use. Our mass is 400 kilograms. The velocity is, or the speed I guess is better, 7,000 meters per second. And then the radius is 1,200 kilometers. Got to make sure I convert that. So I'm going to add a few more zeros here. So 1, 2, 3 more zeros to convert that to meters. And you can see how the units again are kilogram, meters squared per second, like we had in the last problem. Now this is an absolutely huge number, 3.36 times 10 to the 12th kilogram meters squared per second. And that is typical for this sort of application. Again, we'll talk about this more throughout the semester as we get into gravitation.